So I'm here on Thursday. I still don't know what I'm doing with this segment of the channel, but today I'm going to talk about circuits. And my motivation is one, that I have to teach circuits this coming week in my course. And so this is a little bit of a reminder and prep for me. I also have to make a bunch of solution videos and practice videos and stuff for my course and for the homework solutions. I'm going to turn this down just a tiny bit. Hi, chilled cow. I'm turning you down just a little bit locally on my end because it's too loud for me. Okay. So I'm going to talk about circuits, and I'm going to build up the model that we have created in our class for circuits and for their for them calculating them. Yeah, I should check follows. We have a new follower. Thank you, Zemelisk, for following earlier today. Technically earlier today. It was like at midnight Pacific. I can't tell whether it was yesterday or today, but thank you for the follow. As always, if anybody has any suggestions or is hanging out in chat and wants to ask questions about what's going on or questions in general, we're always happy to completely and utterly deviate from everything that we're expecting to do, because that's what good educators do, is we kind of, be a little nimble and be ready to stop and talk to people about what they're interested in, because ultimately physics is a science of being interested in stuff. And we want people to be excited about science. And in fact, my goal with today is to tackle what for me was the least interesting subject in introductory physics that I covered. I disliked it for many, many years. I thought it was horrible. I thought it needed to be cut from physics curriculum across the nation because I don't like circuits at all. That said, in the past few years, I have come around to liking them a little more. Not that much more, but a little more. So let's get into our circuit model for today. So let me clarify a little bit about, like, first and foremost, what we're doing with this model, what we want to be able to do with this model, and what we don't care about with this model. Because at the end of the day, everything that we create in physics and everything that we talk about in physics is designed to answer some subset of questions, and very specifically not designed to answer a different set of questions. So what I want to do with this model is this is weird. Does your OneNote always treat it as a cursor rather than a mouse? Oh, you can't even see it on stream. Interesting. Okay, I'm fine with it. That means I need to pay attention to the fact that you can't even see my cursor.
Can't see it.
That's really frustrating. We should figure out how to fix that. Well, I don't know how to fix it now, but we should figure out how to fix it in the future. So what we want to be able to do is we want to be able to, like, quantify behaviors of elements in circuits. So we want to be able to say, where the energy in a circuit is going. We want to be able to make comments about what kinds of currents are in the system, where energy is going. We really want to just be able to mostly quantitatively or qualitatively. I don't even really mean the word quantify. I really mean qualitatively. So I don't even mean that. I mean, like, qualitatively discuss. There we go. Qualitatively discuss. Because that's the most important thing here, is being able to say something about the dynamics and mechanics of what's happening in the circuit. I don't care about numbers, real numbers, theory, or anything you would do as an electrical engineer. Engineering. I don't care. These are external to my model. If I wanted to know anything about, like, I stick this big of a capacitor and this big of a resistor in a circuit together with this much of a battery, here's what the current looks like as a function of time. I don't care about that in this model. That is very outside of what I care about for the circuit analysis. And frankly, it's outside of anything I care about for introductory physics. if you need to know how to quantify those things and you need to know how to write those down as functions of time, or to look at any other things like voltage dividers and op amps and all kinds of stuff like that, that's very outside the model I'm trying to build, because that doesn't matter to an introductory physics class. If you need to know those things, you could take a class later and learn about them. And as a physics major or as an electrical engineer or anyone who needs to know anything about circuits, you would do that, right? You would take a course later on to specialize in these topics. So I don't care if those things are accessible in my model, because they don't matter. So I'm not even going to worry about it. I really want to focus on some qualitative behaviors. Okay. And so, my mouse was in the wrong, I slid the scene to the side. There we go. I grabbed it on accident with my mouse. Hopefully it still looks okay. What I want to do is I just wanted to scroll down, and it really didn't want to. So let's talk about a circuit. So I am going to introduce the only circuit element that exists. This is a light bulb. And light bulbs are very convenient, and we're going to build our entire theory around this light bulb. Obviously, we're going to have some other symbols in here. So I'm also going to draw single thing batteries. If you're being really careful, you might put 2 of them in there just to distinguish that really is a voltage source. So this is a voltage source. I'm not going to call it a battery. I'm going to try not to call it a battery because it is a voltage source, meaning that this could be any type of thing supplying a potential difference to your circuit. And there's quite a few different elements that can do that, and it's not just limited to batteries. Okay. These are the 2 things these are the 2 primary circuit elements that I'm going to work with. And I am, for the most part, going to only draw circuits with these 2 things in them, because I don't really care about capacitors. I don't really care about inductors. I especially don't care about inductors. These are the 2 big ones that I care about. So here's a question. Here's a circuit. You don't know what's happening past A or past B. You just have a light bulb strung into this circuit. It's just in there. There's wires. The question is this light bulb bright? Is this light bulb bright? And if it is bright, how bright is it? So brightness in a light bulb, from a physics perspective, a light bulb is an pretty ohmic looking device. It is a resistive device. So if you're familiar with the language of resistors, a light bulb acts just as a resistor will. But it is a resistor that physically demonstrates to us what the power dissipated across it is by being bright. And so we can ask questions about circuits with just this light bulb thing. We can stick light bulbs into some place in some configuration of a circuit and try and understand, simply by generating some laws that are true about the system, try and understand how what's happening in the circuit just by looking at the brightness on the light bulb. So if this light bulb is going to be bright, 2 things must be true. And in fact, we're going to treat them as if either could be true, because we're going to develop kind of 2 tools to poke at circuits. Both of them will be true, because if you have one, you're probably going to have the other. But for this light bulb to be bright, there must be some measurable potential difference between these 2 points. If that is true, if there is a potential difference across this light bulb, and that's what we mean is if I measure the potential at A, so I might call that delta VA, delta VBA, and for the rest of today, I'm going to not write the delta ever again. So if you see V's with subscripts, like letters on the circuit diagram, I am talking about a potential difference across that point. So there should be a delta out front. I just don't want to write the delta 1,000 bajillion million times. So if there is a potential difference across this light bulb, then it will be bright. And if the potential difference increases, then the brightness increases. So I'm just positing that this exists, that this is a relationship between these things, and that if I increase the potential difference across this light bulb, then its brightness will increase. And I think that makes sense, right? If I hook up, don't do this in real life, but if you hook up a light bulb to a higher voltage source, it will be brighter. And what it will probably do is explode, because light bulbs are rated for very particular wattages. or at least a very particular range of wattages, and you want to be careful and make sure you plug things into the right sockets. But in our model, we don't really care about things exploding. That's not part of our physics. And so we're just going to correlate that an increase in potential difference is an increase in brightness. There also must be some other feature going on, because what's really happening here, right, is for a potential difference, you're causing charges to become mobile in this wire. And so what is simultaneously true is that not only is there a potential difference across B and A, but there is also a current going in some direction. I don't really care about the sign of that current. I just care that it exists. And if there is a current flowing across the bulb, then that also means it is bright. And we will develop these laws a little bit more specifically in a second. I just want to introduce what I mean by a light bulb. So if you can recognize that there is a potential difference across an item in the circuit, or you can recognize that there is a current going across one of the elements in the circuit, both of those will be clues to you that there will be some brightness here in this light bulb. Okay. So just to recap, the two things that we have here are that if you have a potential difference across your light bulb, it will become bright. And if the potential difference goes up, its brightness goes up. If you have a current across a light bulb, it will become bright. And if the current goes up, the brightness goes up. If you are familiar with circuitry, beyond the point that we're talking about in this simple model, then you will know that the thing that actually controls the brightness of a light bulb is the power dissipated, which in ohmic regions looks something like the current times the voltage. So both of these things will yield brightness, and either of them increasing will increase the brightness monotonically. I don't really care that they're coupled together because I'm going to just treat them as if they're two separate features about the circuit. All right. So let's talk a little bit about what happens at a battery before we start. So I'm a little charge sitting here. And in fact, if I'm being super, super physically accurate, the charge would be coming out of the negative terminal because it's got to be an electron. We don't have positrons flowing through circuits. Although we can track a lack of electrons as if it was a charge carrier with positive charge. And that's mostly what we're going to do when we talk about current, because unfortunately, some people a long time ago decided that current should be a positive thing. And that charge carriers were positive. And like, I can't fault them for that choice. It's pretty reasonable. Minus signs suck. But the charge carriers in a circuit are in fact electrons. And so I should draw this as if things were coming out of the negative terminal. And from here on out, I'm just going to assume positive charge for the rest of my life. So sue me. So I have a little QI here. This QI has gained some amount of energy because it has gone across a battery. So if I, cut this off. So QI, make you a little smaller. QI will have some amount of energy. It's going to have a QI times delta V's worth of electric potential energy that it has gained. The battery has done work on this charge. It has invested in this charge some amount of energy. And that charge is going to move through the circuit. Of course, there are charges all around this QI, but I really just want to track what happens to QI. There's charge all around the circuit, and it's all moving. And this individual QI is going to travel along, and it's going to lead its wonderful little life until it interacts with some dissipative element in the circuit. Once it gets to this dissipative element, it's going to use up some of its energy. And how much energy it uses up, let's call this light bulb A, therefore it will have some voltage drop across it, VA. This is the battery over here, V naught. However much energy, I should say that this was V naught QI. Whether or not that is a positive or negative delta depends on which sign of the battery you're traversing. I don't want to get mired in the minus signs here, but you could if you were being a very specific electrical engineer, which I am not. So I'm neither of those things, in fact. This charge will cruise over light bulb A, and it's going to spend some amount of its energy traversing A. And we call that energy that is spent, well, voltage is not quite energy, but we can say that there's going to be some electric potential dropped across this circuit element, light bulb A. Afterwards, little qi, depending on how many elements are in the circuit, has, well, it's going to have less energy, certainly. And how much energy it has depends on how much it took to get across VA. As I place more and more light bulbs in the circuit, it makes sense to some degree that the charge is going to be interacting more and more with more and more light bulbs. But this charge only has so much energy that it's been given from the battery. So even if I add more light bulbs in here, and I can keep adding them, and I can keep adding them, how much energy this charge has at the beginning and the end is fixed. It's given some amount of electric potential energy, UE, which is just V naught times QI. And by the time it gets right back up to here, when there's no more elements that it is interacting with, this thing now has no energy left over, because it has reached the other side of the battery where the potential difference is 0. And we can develop all kinds of fun things about measuring potential difference on wires. Wires have to be equipotentials. You know, you're only going to drop potential if you go across an item, whatever. I don't really care so much about that. I'm going to introduce a diagramming tool. This is a tool, and in fact, all of the content that we're seeing today is basically the sole ownership of Dr. Paul Emmy, who is a instructor at Oregon State University, which, I'm not doxing myself, I don't give a shit, but I will give fair treatment that a lot of this content was designed by him or people he knew at Washington State or at University of Washington. So this content is not purely designed by me. It was designed in it has been touched by very, very many people over the course of its existence. So I just want to clarify that this is not my content. This is content I am borrowing to some degree. And so I am going to introduce a diagram that we use in this class. So let me scroll down just a little bit more. So I want to diagram what will happen to the potential as a function of stuff, really distance around the loop. And so it's not really even that there's anything on this axis over here. I'm just going to mark some points that are on here. So let's do point 1. Oh, this was a bad choice. The pearlescent pen was a very bad choice. Here's point 1. Here's point 2. And I am, in fact, going to erase all of these millions of extra light bulbs I drew here and just draw in the rest of the circuit, because that's all I really care about. Let's just do that. Yeah, that looks good. Okay, so let me draw back in my light bulb. And then let's look at point 3 as well. So what I want to do is I want to put these points on my axis. So here's point 2. Let's just say here's point 1, here's point 2, here's point 3. I don't really know where along the way. Well, I do know that there is a circuit element, this light bulb A here. I don't really know exactly where voltage drop is going to occur here, or what the voltage drop looks like as a function of distance. And I don't want to be very retentive about getting the shape of this graph right. I don't care. It's not part of my model. I just want to be able to diagrammatically represent what's happening to the potential around this loop. So at 1, my little charge QI, well, it's going to have some amount of potential. I don't know. Call it V naught. It's got V naught worth there, right? It's fresh out of the battery. It's ready to conquer the world. What's going to happen as I get to 2? Well, at 2, I haven't encountered anything, right? So I still have a potential of V naught at point 2. Voltage short. I said battery again. I'm gonna keep saying battery. I'm gonna resist my own rules and probably continue to call it a battery, because I just can't speak correctly. It's a voltage source. It's a battery. Oh, that's awful. Oh. I'm gonna be a battery. Be a turi. Anyway. Where was I? I was in the middle of justifying that I don't care about the exact shape of this. If there's only a single element in this circuit, well, how much energy is this charge going to drop across this light bulb if it needs to come back to the negative terminal of the battery with no more electric potential? Well, all of it. So somewhere in between 2 and 3, it's got to go back to 0 until it hits the voltage source again. Which I guess I can give that a point as well, that it's going to be 0 back here at the negative terminal of the battery. So I'll give that a point as well. Oop, wrong color. Oop. Here's 0.4. And so something has to happen in here. Changes in potentials are probably not going to be completely discontinuous. I would make the argument that because batteries are made up with continuous filaments, it's probably going to be dropping voltage somewhat linearly across the body of the object. I don't care. It looks like that. Sue me, right? Like, it's got to look something like that. The exact shape of that is going to depend on how you model the interaction with the light bulb and what's happening in its spatial extent. And, like, I could go on forever about all the things you would have to consider if you were going to actually draw the shape of that thing accurately. But accuracy is outside of my model. In fact, I'm going to scroll up and I'm going to write accuracy in here because it is outside of my model. I don't care. Okay. This thing is called a voltage diagram, and we're trying to make it happen. It's not going to happen, but this is a somewhat useful way to break these circuits down, and we're going to continue to draw these as we proceed through this content. But yeah, I wanted to introduce this fun little diagram. So here's a question. What happens to the charge as it goes across VA? Does the charge get consumed, or is it just energy that gets consumed? I mean, charges can't be created or destroyed, right? So as the charge goes across VA, charge moves across VA. It's not going to get destroyed. That's actually a pretty nice feature, right? If the charge doesn't get consumed, that actually tells us something very special about one kind of quantity that we can track here. I mean, there's two. If you've ever seen circuits before, you know that there are two things that we're primarily concerned with indexing in the circuit, and that is the potential difference V and the current I. The fact that the charge moves across VA, it's gonna not die as it goes across the light bulb, and that implies that current is conserved to some extent, in some way, in some fashion. We're going to develop this a little bit more, but I want to formalize what we set up here with the battery first. So small segue, not really a small segue. So we have this statement that means that the I is conserved, but follow up, voltage is being consumed. And I'm going to give that scare quotes because I don't really want to say consumed. It's not like it's being eaten. It's not like there's a big voltage monster that's eating all the voltage. But that is pretty typical parlance that we have for talking about circuits. That is pretty common, I would say, for pretty common language. So if the voltage is being consumed around the circuit, this is going to tell us something really important. That if I have some number of objects in my circuit, if I added up the voltage drop across each one of these, so there's going to be some voltage that I gain or lose around every element. If I go across a voltage source, that's going to increase my potential. If I go across a circuit element that is not a voltage source, I'm going to lose some potential. And if I add up all the potentials as I go around the circuit, for every element that's present, for how many of them are, however many there are, let's say there's n, this better be 0. And this must be 0 around any path I traverse in my circuit. This has to be 0 around any path. And if you desperately wanted to attach an old dead person's name to what this thing says, if you like can't learn science without there being an old dead like Swedish or Dutch person's name attached to this, because I guarantee that's who did this because of all the fun colonialism and imperialism of the past. This is called Kirchhoff's law. This is Kirchhoff's loop rule. If you're an electrical engineer, you call this KVL, Kirchhoff's voltage law. And there's, well, actually, this is KLL, Kirchhoff's loop law. I don't know. Kirchhoff's law? I think it's double F with a CH. It's called Kirchhoff's law. I'm just going to call this a loop law, because I don't care that it has Kirchhoff's names attached to it, because I'm a rebel. And I'm not going to call it Kirchhoff's law ever again. It's just a loop law. This has to be true, and this is a consequence of what we said earlier about the charge losing energy as it goes across the object. It must pay, the charge must pay energy to move across a resistive element or a dissipative element in a circuit. That has to be true. Okay, let's do the consequence for the I conservation too. So these are my two big ideas. So one, that the loop law is true, and two, that if I add up the currents going into some junction, where a junction looks like right here. So if I have some I in and going this way, and I have some I out 1 and I out 2, for however many I outs I could draw, for however many pieces, however many splits there are to this junction, these have to be the same. I in equals I out. This is purely a statement of charge conservation, because charges don't get created or destroyed in circuits. And if they are being created or destroyed, hit me up, because you have something I want to know about. This is just true, right? To create charge, you have to do some really screwy things. And in fact, it's a very fundamental law about our universe, that charge is conserved, or at least it should be. And what we're going to call this, the junction rule, because this is what happens to current at junctions. But like, again, I don't actually care that this is attached again to Kirchhoff's name. It's like, all the science I'm doing here is completely agnostic to the fact that any of these people came up with these ideas, because it's just science now. Okay. So these are our two big laws. 1 and 2. My goal for today, as much as possible, is to only ever think about the first one, where possible. I'm going to hit you with just a little bit more information. I'm going to hit you with a correspondence. Light bulbs are really not ohmic. There is no such thing as Ohm's law in my course. There's no Ohm's law. We're never going to talk about it. So all of the questions that I'm going to write down, if you were to respond to any of them with the statement V equals IR and to try and form a correspondence from potential and current, you're wrong AF. Okay? Like, don't do this. Bad. This is not real. We're not going to use this. It's not that it's wrong. It's just that it's outside of our model, and in fact, it's pretty much wrong in every single case that you use it, because it's a really, really bad approximation for basically every electrical anything out there. That was the only thing I learned in my graduate E&M course. Sorry. Was that Ohm's law is like Ohm's loose approximation for ohmic devices, which it's a mouthful, so we just call it a law, but it's almost never true. So what we're instead going to say is that if voltage, if the resistance of a circuit goes up, then for a, at constant potential difference, if the resistance of the circuit were to change, in this case, increase, then as a consequence, we will say that the current decreases for constant V. In reality, the relationship between current and voltage for any device is you have to undergo, or you have to do some treatments with like hysteresis and stuff. And it's really, really, really nasty to actually come up with satisfying descriptions of these two things. So we're like not gonna do that. Instead, what we will do is we will very specifically form a correspondence between an increase in resistance will mean a decrease in the current going through the circuit. But every question that I think about doing here today, I am very specifically never going to use Ohm's law. And I want to construct an entire, what's it called? Like an entire physical model that has nothing to do with Ohm's law. Okay? So this is the goal. I am currently looking at a problem that I'm just going to copy, or I'm going to copy some amount of into here. And I could just do it with copy paste, but I don't want to like show the mildly copywritten content. So I'm just going to pretend that I'm just looking at it over here to the side. So let's do some practice with this idea, with these two new laws. And I'm going to give myself a big old beautiful pearlescent line. Oh God, that's gorgeous. I'm going to give myself a beautiful pearlescent line, space colors. Although I feel like green doesn't happen very often in space. So, fine. All right, here's a loop. Got my voltage source over here. I'm not going to give you any numbers. I'm just not going to say anything. All right. So, what do we want to talk about in here? I already said most of the things that would happen in this situation. So let's actually not do this one because I already talked about how to build the model for this one. So we're instead going to talk about a separate case. Okay. There we go. All right. So, can we say anything given this situation about the potential difference across light bulb A and light bulb B? Well, let's draw some loops. So I can pick, and I'm going to usually write them in this way. I'm going to draw little circles for 1 and 2 going around the outside. So that's just the loops I'm doing. So for loop 1, I can write down the loop law, right? So I'm going to encounter a potential V0 coming out of the voltage source, and I'm going to hit that first. So I'm just going to start over here in both cases, right beneath the battery. Voltage source. I'm going to continue to mess that up. So I'm going to, starting off at the point, I'm going to go correctly, the correct direction over a battery from negative to positive is going to give me a plus VA. Then I'm going to go over VB. And then I'm going to come back to the point that I started at. And once I get back to the point I started my loop at, no matter where I started my loop, when I get back to the point that I started at, it better be 0. Well, what is the, ooh, it's not VA. It is V0. I'm bad. I'm bad at writing. This is V0. Okay. So that must be true. And if I go over here to loop 2 and do some analysis, starting at the same point, but going around the outer loop, I get V0 plus VA equals 0. Now, can I say anything about the voltage, the brightness difference between bulb B and bulb A? Is, so how does the brightness compare? Well, if I look at these two equations, the only way that these equations can both be satisfied at once is if VB equals VA. And those have to both in turn equal negative the voltage coming out of the source. Great. I mean, that's exactly what we want from this model, right? Like, the fact that these two have the same voltage across them, remember, part of our model was that voltage corresponds to brightness. So, if these two have the same voltage drop across them, then they're the same brightness. So, must be the same. Because VB equals VA. And we know that from doing our loop laws. So that's actually Really nice. We didn't need to know anything about resistance. We didn't need to know anything about current. All we used here was loop law and what has to be true about systems of equations. Since V naught is the same and 0 is the same in both of those equations, VB and VA must be the same number for that to work in both cases. God, staring at the right monitor is like ruining my neck. Jeebus. Okay. So let me move on to another one, because this problem was very boring. So let's make a more fun one. Let's get into some fun circuits. So let's do another one. Sorry, I'm just trying to copy this picture over here. In principle, I know all of these diagrams because I've worked on them a million times and blah, blah, blah. But I'm not going to try and draw them by hand or from memory because I know I'm going to mess them up if I do that. All right. So here's a A, here's a B, here's a C. So, question, how will A and B change when the switch is connected? Well, you might be able to form some initial ideas about what's happening in the system before doing anything, but let's draw some diagrams. Let's draw some loops, right? So let's do, let's look at loop 1 here before and after the switch is closed. So on loop 1, well, start here at my orange point again. I'm going to go around A and B and come back. So I know V naught plus VA plus VB equals 0. This is before I have closed the switch. So I'm just going to make sure I'm remembering that this is before I've closed the switch. And that must be true. So now if I do the after for loop 1, what does my Kirchhoff's law look like? What does my loop law look like? Well, it's V naught plus VA plus VB equals 0. This does not tell me that these voltages are the same. Because there are two circuit elements in here, I can't make the same argument I did before. Because all I know is that the sum of VA and VB in each of these two situations must be equal to V naught. That doesn't mean that VA equals VA before and VA after are the same, and VB before and VB after are the same. So what I need to do is I need to draw more loops. The secret to doing loop law questions is quite literally drawing more loops until you have done the thing. And you just keep doing that over and over and over again. You can draw as many loops as you need to until you find the answer. Usually there's a smart loop to pick. Yeah. So let us do a loop. Oh, there is a very smart loop you can pick after closing, but I'm just going to keep going in what I was doing. So VB and VC, well, what loop do I want? Oh my God, my neck. Sorry, give me just a second here. I need to stretch a little bit. My neck is very, very stiff from doing like 4 hours of various things that look exactly like this today. Okay. So, let's do a big one on the outside and just see if we learn anything from that. So let's call that loop 2. So loop 2, this is of course after the switch is closed because otherwise I'm not going to be able to like see anything here. So I'm going to hit V naught, I'm going to hit A, that's a VA. I'm going to drop some across VC, and then I'm going to come back to the battery. So that better be 0. Okay. So if this must be true, if V naught plus VA plus VB is true after the switch is closed, and V naught plus VA plus VC is true after the switch is closed, then to me, it looks like VB and VC must be the same. So these two equations together imply that VA equals VB, or no, not VA. VB and VC must be the same. That makes sense to me, because a clever loop that you can draw in here is actually to start at this pink point here and traverse the inside loop. if you did that, you would also find that VB and VC had to equal 0, because whatever I gain going across VB, the wrong direction, I need to drop across VC. So that's kind of cool. But I'm not going to talk about that loop. So the question is, what happens to the brightness of bulb A and bulb B when the switch closes? Well, it looks to me an awful lot like, at least for bulb, how do I want to say this? I'm trying not to go to current reasoning unless I desperately need to. Did I just mute the computer somehow? I hit that. There we go. There's a mute button on the tablet that my hand hit. Oops. So what I want from this situation is to understand what's going to happen to the brightness at bulb A. And I'm really, really trying to do it without invoking current reasoning, but sometimes you need to talk a little bit about the current. To me, it doesn't look like I can say anything satisfying about these equations right off the bat. If VB and VC need to be equal, is there another loop I can draw that's interesting? No, these are the only loops I have access to. Okay, well, I guess we can use current then. I don't want to, but I think we have to talk about the current here. Oh my god. Okay, I will move you closer in so I don't do that again. Jeez, keep muting everything. Okay, so let's talk a little bit about what happens to the current when the thing closes. So, when the switch closes, they're at this junction, whatever current is coming out of the battery now needs to split between B and C. Because there are more paths available for the current, what's actually going to happen is that for a given potential difference, if I add in B and C split in parallel like this, which we really haven't actually discussed in our model yet. So, we didn't talk about series and parallel yet. Well, we talked about series. We didn't really talk about parallel. So I guess I need to diverge for a second here. Well, we talked about, let's go actually back up to this case from, did I not have a double case in here earlier? Oh, here, it was right above. What we didn't talk about here is what happens to the current in this case. So if I add this second light bulb in here at A, the battery is going to be able to put out more current. And if you're a very physics inclined or a very physics or circuit inclined person, then you can understand this through the concept of equivalent resistance. If the two light bulbs are in parallel with one another, then they're providing less resistance to the circuit overall than one battery individually, or one light bulb individually. And certainly less resistance than the two light bulbs in series with one another if light bulb A was like down here beneath light bulb B. So what I know as just a correspondence is that as I add elements in parallel, I know that the current from the battery needs to increase, essentially, because I'm changing the total amount of resistance that the battery sees in the circuit, meaning it can output more current for the same potential difference. That's kind of nice. So when I add C in, the equivalent resistance of this circuit has actually gone down, because what was light bulb B is now split between B and C. Because the current has gone up, so adding in C increases the current out of the battery. So some amount of current is coming out of this battery, and I naught is going to go up when we add C in, when we close the switch. So because I naught goes up, that means that brightness at A needs to increase, so A gets brighter. We know that not from any voltage loop rules, because our voltage loop rules did not actually tell us anything about the brightness of bulb A, right? What happened for the brightness at bulb A is purely being controlled, or at least in our model, we can only investigate it through the current. So because the current went up, the voltage drop across A had to increase. And what that actually means is that since the voltage from the battery is the same and VA has gone up, VB must go down. Because if I draw this loop, this loop is still true. Loop 1 after here, this loop is still true. And so if VA is increased after the closing of the switch, then VB must decrease because that's how numbers work. Now, this all seems, so my prediction is that increases I naught, A gets brighter. Consequently, B gets dimmer. And C increases in brightness because it wasn't bright at all before, but like we're not asked about C. So what I'm actually going to do is I'm going to pull up a FET simulation because I can do that. And what I'm going to do is I'm going to stick in a battery to my circuit. I'm going to stick in a wire. I'm going to stick in another wire just so that everything looks the same. I'm going to put a light bulb here. I'm going to stick in one wire there and another wire here. Light bulb. And you can, of course, reduce this circuit to be a little less complicated than the way that I'm currently drawing it, but I don't care. I'm just trying to make it look accurate enough so that no one's going to say, like, hey, that's not the same circuit. Because sometimes people do that. Hey, okay. So they're lighted up like that. Can I pause this somewhere? I can't. I just can disconnect that. Okay. And then I'm going to put another light bulb over here. This is now in parallel with this other one, right? Except those are not in parallel. What I need is, I need this to do like that, and this does that, and then now this goes here. Okay. I'm going to bring this down just a little bit so it's a little more obvious. Okay, so this is the light bulb that we encounter before the junction split. Then the junction splits going to 2 light bulbs, and then we go back to the terminal. I could massage this a little bit to make it look slightly more like what we were dealing with in the problem. How about that? That looks pretty good. That's pretty close. And so let me, I want to disconnect this wire. Okay. So this is the situation we have before the switch closes. You can see that A and B are the same brightness, and you can tell the brightness from this simulation by the length of the shiny arrows. Are shiny lines coming off the light bulb. That's kind of cool. So now my prediction was if I click this together and I attach the second piece, what I'm going to see, actually, I don't want current. Go away. What I predicted I would see is that A is going to get brighter and B is going to get dimmer, but B and C need to be the same brightness. I did a thing. That's exactly what happened. If I disconnect this one more time, my prediction was that bulb A will get brighter, bulb B will get dimmer, and B and C will be just as bright. Voila. And that has to be true. And we know that just from our simple little model. I'm super proud that I actually managed to do that correctly after a year of not doing circuits. This stuff is usually hard. Voila. This stuff is usually pretty hard to investigate, and it's pretty opaque to learning anything from it. But this one looked like it worked perfectly. Cool. Yeah.
Like having everything.
Mm-hmm.
Makes sense.
All right. Yeah, no, I really like that. I really like that FET simulation. I think it's wonderful. Maggie was just commenting how much she likes that FET simulation, and I do too. All right. I'm bored with these circuits. So let's do something that literally no introductory electrical engineering courses ever do, because this is all pretty old hat right now. If I gave you Ohm's law, you could have figured all of these things out in seconds without a problem. So let's start doing some more fun circuits. Here's 3 circuits. So we got A. So this is voltage source A. Here's light bulb 1. Here's voltage source B and voltage source C. Here's light bulb 2. And then we got this again. 2 light bulbs. And so here's 3 and here's 4. And I guess this is D and E. So, how about some questions? Let's predict the brightness of these bulbs. Rank brightness. Well, remember that brightness is given by voltage and current, but let's talk about voltage. They have been ranked. Maggie is ranking them. Yeah. So, the higher, so let's assume, as always, all of the light bulbs are identical and all voltage sources are identical. So here, for light bulb 1, I'm going to go across one of my voltage sources and drop however much that is across light bulb 1. So however much is coming out of the battery is exactly the amount that 1 drops. So at the very least, 1 has a delta V. So these, I'm just going to tabulate delta V's over here. 1 has 1 delta V. Bulb 2 has both the potential differences of B and C in the loop. And so bulb 2 must be dropping the potential difference given by voltage source C and B. So this has 2 delta V's worth of potential dropping across it. D and E, I'm going to gain 2 potential sources worth, or voltage sources worth of potential, and then I'm going to drop it across 2 light bulbs. And so 3 and 4 are both getting 1, are both seeing 1 drop individually. We could see all of that just by doing my loop laws and knowing that they must be the same. Since both of these must drop the same V, they both must drop exactly half of the voltage being supplied by the voltage sources, i.e., they're both dropping one source's worth of voltage each. So that to me looks like brightness 2 is greater than brightness 1, which is equal to 3, which is equal to 4. So that's nice. Let's talk about the currents. Well, can we say anything about the currents through these objects? So question, rank current going through each battery. So remember our little analysis of current said, all right, well, if basically current is proportional to the voltage being supplied to the circuit and not disproportional, inversely proportional to the resistance of the circuit. So there's some voltage source A for light bulb 1, and there's 1 light bulb in the circuit. So let's say that the current through battery A has magnitude 1. It's 1 I naught's worth. It's 1 I's worth. And we're just going to rank the other ones in terms of how many multiples of I naught it gives. Okay. So now for circuit 2, there are 2 voltage sources and 1 resistive element. And if you say to me, boy, it sure looks like that's going to be 2 I naught's worth of current. Yeah, you're right. I through B equals I through C, which is going to be something like double the original current. And of course, I'm not calculating these explicitly through Ohm's law because of course I'm not doing that. That would be cheating. That said, I am sort of using a little bit of ohmic reasoning to get exact factors. I could simply say that this has to be bigger than IA and not put a factor of 2 out front, but the electrical engineer police aren't going to come after me, so I don't care. And again, in D and E, the current through source D is going to be equal to the current through source E, and because there are 2 voltage sources and 2 batteries, I think it's pretty nice and easy to tell that there's going to be 1 I naught's worth of current through there, which tells me that IB equals IC is greater than IA equals ID equals IE. That ranks the current through those devices. So that's kind of cool. Excellent. Go on. Make them harder. Hell yeah. Here we go. Sorry, I'm just looking and we're finally getting to some cool circuits. Sorry, just give me a second while I'm looking at these to try and look at these. Okay. Next circuit. Let's just keep going. A circuit school, perhaps. Yeah, that's kind of a mood. Thanks. Thanks, 8-Ball. So let's do... I'm just gonna keep making these, because that's super fun to do. Is it like... Is it compound at all? Oh, it's, Oh, that's cool. It's like the Chowder effect. It's like a scratch thing. There's like a single background that it's emulating in the background, and that's neat. That's a really smart way to design that, rather than having to calculate the color at each point in the pen. Sorry, I'm very distracted by how smart that pen design is. Anyway, new circuit. I should be drawing. Hello? Maggie? Help? It's not letting me change pens. Hello? OneNote? Hello? I think I just have to close OneNote and open it back up. Exciting. Okay. I can't even erase either. Ooh. This temporary distraction in our program brought to you by Microsoft, creator of the most cursed software imaginable. Microsoft, we know better than you, and if you tell us otherwise, we're going to repossess your computer. I'm just going to try and open up OneNote again and see if it will be happier with me. Voila, there it is. Cool, great, excellent. Next circuit. Oh, that's not there. There is a second battery. What am I doing? That looks to me like the circuit I'm trying to do. I'll number these just congruently with the other numbers we've been doing, and this is going to be H and I because we're just keeping the letters running as a running total. All right, and the question is, well, there's a lot of questions. Let's just rank the voltage across the bulbs. I guess that's fair. So rank V. Well, there's 2 voltage sources worth of stuff coming out of H and I. And if I go over light bulb 7, and I draw this inner loop here, which you can't even see my cursor. There we go. If I go over H and I and I go over light bulb 7, 7 must drop an H and I's worth of voltage. If I go over loop 8 and 9, they also must drop an H and I's worth of voltage. That said, 2 light bulbs on the right half of the circuit, 1 light bulb on the middle part of the circuit. You bet that V across 8 is going to be equal to V across 9, but both of those are going to be less than the voltage drop across 7, because one thing versus 2 thing. There's not really any arguing around that point. It's just that's just what that's going to look like. It has to be. And according to our brightness ranking, that implies that V8 or that the brightness of bulb 8 and 9 will be the same, and they will both be half as bright as bulb 7. And so if I come over here, I can actually come into this thing, and I can delete some... Where's my garbage can at? Took me a second. Let me just toss some of this out really quick just so I can, like... Okay. So my new circuit has a light bulb here. It's got... Oh, hey, no, bad. Disconnect. Let's grab another one of these. That's going to do something like this. Here's one light bulb. Disconnect. Here's another light bulb. And I'll put a wire in between them just so that they're slightly more obviously distinct. I don't need this one. Now what I have is I have 2, and you know what? Even for the sake of just being as jovial as possible, I'm just going to rig the second battery up in there. Cool. And so now what I can do is if I connect that part, nothing's going to happen. So now what I can do is I can attach the circuit, and we'll see whether or not our prediction that this middle bulb will be brighter than the other 2 bulbs will be true. At least that's what our loop law told us had to happen. And voila. Kind of hard to see because I doubled the voltage, but you can tell that this light bulb is definitely got bigger vectors than the other two. Because it should be brighter, and it should be twice as bright. There's not really a good way to encode that in the simulation. Like, I guess I could take out a tape measure and try and actually, like, measure it. But what I could do is I could take a voltmeter and stick one probe here, and see that I'm dropping 18 volts because these are both 9-volt little double A's. And if I look at the voltage drop across one of these little guys, should be 9. Hey, look at that. Science. Okay, so I'm going to leave the simulation alone for a second. I'm going to disconnect it just so it's eating up a little bit less of this. Actually, it's not eating up anything of this computer's processing power because Maggie's computer is like 8 times better than mine. And like 7 times newer. And now graphics card prices are the same as kidneys, so welcome to the Bitcoin era, everyone. All right, so let's do another circuit. I don't want to do that circuit because that circuit's boring. So I'm going to go to the complicated ones. All right, so that was our, yeah, thank you, Bitcoin. So that was our brief little introduction to easy circuits. So, much like our relationships with literally everyone over quarantine, let's get complicated. So, new circuits. We're going to do circuit 2 and 3 and whatever I want. So, I'm going to grab these two. So, let's compare the brightness here between that circuit, this circuit, and this circuit. So let's just say that this is light bulb 2, light bulb 3, and light bulb 4. And all of the batteries in here are the same voltage source. So they all have identical batteries, identical light bulbs. Can we rank the brightness of these three? Well, can we? Yeah, yes, the answer is yes. So if we look at loop 2, or the loop for, let's call this actually circuit 1, circuit 2, and circuit 3. Yes, that's confusing. I intend it to be. Circuit 1 contains a voltage source and a single battery, or in a single light bulb. This means that however bright this thing is, it's going to be 1 bright, because I'm just going to scale everything to that brightness. So circuit 1 is 1 bright. So 1 is 1 brightness unit. Okay. Circuit 2, I muted my computer again. Oh my goodness. That button is so sensitive. Just like my arm passing anywhere over it, it mutes immediately. Jeez. Okay. So circuit 2 has 2 voltage sources and a single light bulb inside of it. So that means by our loop laws, circuit 2 must be too bright. Too bright, too furious. How much voltage? What's happening in circuit 3? This is complicated. What does this actually look like? If I do my loop law, what do I get? Well, if I approach a battery the wrong way, what happens? So if I do my loop law, from here, I'm going to go across a V0. I'm going to go down a V0, and then I need to drop whatever over light bulb 4, and that needs to be 0. Can anyone tell me what V4 must be for this equation to be true? This exam is worth 100% of your grade in the course. It's got to be 0. So this implies that 0 plus V4 equals 0, which of course means that V4 is 0. Because of course it is. You put 2 batteries backwards in a circuit together. What did you think was going to happen? Don't do that, right? Like, let's do this. I'm going to make this circuit by flipping this battery, and then I'm going to connect the light bulb. And if I'm right, and well, it's not going to explode, not yet. If I'm right, what will happen is nothing. Ta-da! And if you're desperately convinced that it's because of that thing there, it's not. Nothing happens because as I gain V over one of the batteries, I'm going to lose V over the other battery. Of course, if I were to switch both of them around, then the thing can be bright again, but that's not what I have. To make it match the picture, I guess we'll do that. Not that it matters. So that's kind of cool. All right. Ooh, that wasn't what I wanted to do. I wanted to bring one note back up. Okay, so that has to be true. So the brightness must then be that brightness in circuit 2 is greater than the brightness. What am I doing? Brightness in circuit 2 must be greater than the brightness in circuit 1. Which, of course, is greater than the brightness in circuit 3, which is equal to 0. No bright. No bright in that bulb. 0 bright. Okay. Let's get some much more funky circuits going on. So we have done quite a bit of easy circuits up until this point, and let's get into some much more complicated ones, or at least some ones that like you might not immediately know what's going to happen. So next we will do this circuit. Where I guess I can be a little bit more obvious about what's happening. Really hard to draw. Okay. So what does our little analysis mechanism tell us is going to happen over here in circuit 5? This is circuit 5. So what's going to happen over here? Well, I have a V naught here, I have a V naught here, and I have a V naught here. I'm not really giving them signs because I'm not associating a direction with anything yet. As I go across V, well, I'm going to gain a V naught here, I'm going to gain a V naught here, and then I'm going to lose a V naught here. So how much, did I orient this correctly? Yeah, I think I did. So how bright is this battery? How much voltage, or how bright is this light bulb? How much voltage is light bulb 5 dropping? Well, if I do my loop law, I'm going to gain a V naught, I'm going to gain a V naught, I'm going to lose a V naught, and then I'm going to drop whatever I drop across V5. And then that has to be 0. Plus V naught minus V naught is the same as this. So this V5 is dropping 1 battery's worth of voltage. Well, that makes sense. We just stuck 2 batteries of opposite terminal into the circuit. And, well, I mean, my gut is telling me that if I do that, if I stuck another battery in here and then close the circuit, it should be 1 bright. So what I could do is I could detach you, and I could just grab another battery and stick it right here and stick this wire here just to show what 1 brightness light bulb was again, and these are the exact same size. So that's what should happen, right? If I add and subtract to the electric potential as I go across a battery positively or negatively, it makes sense that the brightness is going to go up or down. That's kind of cool that we can do that. All right, let's do something even grosser. We are just going to monotonically increase in grossness as we go, because we're physicists here, and everything needs to be as complicated as humanly possible. So let's stick a light bulb in between batteries. I can do that, right? I shouldn't. You shouldn't do this, by the way. But I'm not your boss, so you can do whatever the hell you want. So here's a 6. Attach that to that battery. So I have a V naught here. I have a, wait, did I hook that up to the right number? Yeah, it should be 3 batteries. Okay. So what happens if I go from, say, I don't know, this orange point through what we got going on? Well, do my loop law. I'm going to gain a V naught. I'm going to gain a V naught. I'm going to gain a V naught. And I'm going to lose a V naught. And then I'm going to drop whatever I'm going to drop across the light bulb 6. Well, that implies that V6 is dropping 2 V naughts worth of stuff, because of course it is. Oh, except. Wait. Hold on. I need to be actually careful here, Nope, I'm good. So this is actually a really interesting point to comment on what I'm getting. So I was concerned there for a second because I remember what students often reply in this situation. So here's a student response, which I think is very fun. So students look at diagram 6 here, and they say, um, bulb 6 is disconnected from the circuit. Is this statement true? So what a student may say, so let's just say for the sake of argument that a student has supplied the response, bulb 6 is disconnected from the circuit. Therefore, it has no brightness because there's no current flowing through it. How could there be current flowing through it? There's no wires connecting it to the rest of the circuit, right? Like, what? What's happening? How could this possibly work? Well, we can load up our little simulation, right? Let's switch this battery around. Let's disconnect this just before anything happens. And I'm going to disconnect you, and I'm going to disconnect you, and I'm going to disconnect you. And what we had is we had one battery that was flipped before coming to a light bulb, before that light bulb hits a series of 3 batteries all going in the same direction. So when I hook these little friends up, if the student's response that the light bulb is disconnected from the circuit is correct, then this light bulb will not light up at all. If that reasoning was incorrect and there's something more complicated going on in the circuit, then this light bulb will light up. Can I get some votes in chat from the one mod who's here? Add. Well, I swear she actually responded to that before the stream delay got over there. So that was a legitimate response I watched. Yeah. Of course this light bulb is going to light up. So what's wrong? I did this again. What's wrong with this argument that bulb 6 is disconnected from the circuit? Well, we don't have a tool that says anything about analyzing a finite amount or a finite duration or segment of a circuit. How do we analyze circuits? You got to go around the whole damn loop. You got to go around the whole damn loop, and you have absolutely no way to analyze a particular segment of a circuit. You just don't get to. You're not allowed to. It's illegal. The electrical engineer police will come after you if you say that. So this is an incorrect argument. So this is incorrect. You can't analyze individual segments of circuits. You can through some other things that like we're not going to talk about in here, through things that are more complicated than what we have here. Can't analyze the individual circuit segments, only loops. Give me the loops, brother. Yep, loop memes. Yeah, those are high quality memes. Those are almost as good as the moth memes. Just all high quality memes all around. Thank you, Maggie. You really are a peddler of only the highest quality memes. All right, so that's all great. All right, time for some fun stuff. Let's get to some good ones. Lamp. I'm bad-mouthing Lamp. The moth memes are garbage. Not that anyone who's ever made a moth meme before is garbage. I appreciate the labor that you've done putting memes out there, but the actual content that's in there is very poor. But I appreciate you for making memes, person out there who makes moth memes. Okay. All right, I'm trying to copy this one, and I need to get the diagram right because the diagram is really, really important. I mean, the diagram for all of these is important, but like, yeah, okay. So I have bulb B over here. What am I doing? Bulb B, and I have bulb A over here for this new circuit that we're talking about. And you can see the orientations of the batteries. So bulb A here has the batteries kind of in this upright position. Bulb B has one of the batteries flipped. And our I'm going to read a couple predictions that some students made about this. These are fake students. They do not correspond to real students, but they are arguments that we have heard from students many, many times over the years. So, student A looks at this. We have asked two fake students to analyze this circuit. Student A, or student 1, says bulbs A and B are in parallel branches. Since bulb A is connected to a positive and negative battery terminal, the left branch is a complete circuit, and so bulb A will light up. The right branch is not a complete circuit. Therefore, bulb B will not light up. Say that one more time. Bulb A is in a complete circuit because it is connected to a positive and negative terminal of a battery. Bulb B is not in a complete circuit. Therefore, bulb B will not light up. I actually love the circuit content that we have for this. It's fun, and it only gets more fun from here. I should have gotten to this a little faster. Okay, so student 2 says, I agree. Bulb B won't light up because it's connected to two positive terminals. Since both positive terminals have to be at the same potential, there's no potential difference across the bulb B, and it won't light up.
Is a battery? Is it in a battery?
Well, how do we look at these things? This is not a pleasant thing to analyze from the perspective of Ohm's law. We don't care about Ohm's law. Let's just write down some loops. I'm going to start at the orange point. I'm going to go across a V naught. I'm going to go across the light bulb A. I'm going to go across another V naught. I'm going to go across another V naught. And I'm going to go across VB, and then I'm going to go the wrong way across the terminal. This tells me that I have, what do I have left? 2 V naughts plus VA plus VB equals 0. These light bulbs are identical, right? And they're all in one circuit, right? So if I have identical light bulbs that are in a single branch of a circuit where the current must be the same, since we're in one loop, since no junctions, how about that? No junctions. VA must equal VB, which implies that they have the same brightness, equal to 1 negative V naughts worth. Now, if our loop law is correct, what that actually means is that both of these students are completely incorrect. They were using good reasoning, but their arguments were not sufficient. So, if my loop law holds true, I should be able to go into my circuit building tool, and I should be able to see both light bulbs light up with the same brightness. If they don't light up with the same brightness, then we have a problem, right? That's going to be real bad. And so, let's test it out. Bring up my circuit thing again. Let's just reset everything. So I have one battery. I have 2 battery. I'm going to stick a light bulb here in between them. I'll put wires on them in a second. Then I'm going to go around. Then I'm going to encounter a third battery like this. And then I'm going to encounter one in the wrong direction here. Ooh. Get rid of the current because God, no current allowed. I just don't like the current view. Sorry, connecting everything with wires takes a second. Okay, so now, if the students' predictions were correct, since they agreed with one another, that means that because this battery over here has no potential difference, or this light bulb has no potential difference across it because it's connected to 2 positive terminals, that means that this light bulb will not light up if the students were correct. Further, if the students were correct, the left light bulb will light up, but the right one won't, because this thing is connected to exactly 1 V naughts worth of potential. All right, let's see what happens to their prediction. Whelp. Boy, this right-hand bulb to me sure looks an awful lot like it's connected to two positive terminals of a battery, and yet it's got some potential difference across it because it's bright. Well, like, no duh. It's a circuit. It's got batteries and voltage and light bulbs in there. Current's flowing. Of course it is. Like, it's a circuit. How is it that that light bulb isn't going to be bright? You're telling me there's no current flowing in there? What mistake did these students make? Clearly, they did something incorrect, right? Some part of their reasoning doesn't work here. So, do batteries just kill one another? You make the currents flow backwards through the battery. I'm making current flow backwards through this battery here, and this one, and this one, and this, conventional current. Sorry, there we go. Those were electrons. Yes, this is a bad thing to do to a battery. You shouldn't do this to batteries. But this is absolutely how loop laws work, right? It has to be how loop laws work. I come over here to my notebook. I did a loop. I did a loop around this thing. I did the loop. It goes around, and as I encounter batteries in the correct direction, I gain potential. And as I encounter batteries in the negative, going across them the wrong way, I lose potential. But that has nothing to do with these being isolated segments of a circuit. Let's go back to this statement over here. Incorrect. You cannot analyze individual circuit segments. You may only talk about circuit loops. And that is the mistake that these students made. Eels and escalators. You may not. Yeah, a potential. Okay. I mean, we can talk about batteries as escalators, right? If I don't want to encounter escalators in the wrong direction because that might do something weird to me. But all it's doing is it's changing the value of potential as you go across it. It's not that the positive terminal of this battery is at 9 volts. That's not what that means. That's not what that means at all. What it means is as I traverse this battery, my charge gains 9 volts times Q worth of energy. It goes up an escalator. If I go the wrong way across a battery, I go down an escalator 1 QV naughts worth of energy. But that doesn't mean that my energy at that point is 9 volts. Because then the argument would be that both of these points are at 9 volts, therefore there's not a potential difference across them, therefore the battery doesn't light up, and that's not true. That's not how circuits work. All you know is that going across that battery, you gained 9 V naught Q worth of energy, and that's it. Yep. Sucks. It's pretty cool, though. All right. So, let's make some even further messed up circuits because we've still got some time here. So, like, I'm just going to keep making even grosser grosser circuits. So, ooh, that's a big positive terminal. Oh my god. Okay. Let's go here. I got a light bulb and I got a light bulb. See, like, I actually low-key love this light bulb formalism. It really, really, really makes the engineers in the room hate us. Absolutely hate us. Because we ask questions that they can't do through, like, node analysis, and they get really mad about it. They're like, what do you mean I can't use Ohm's law and mesh analysis? I've already taken 4 electrical engineering classes. I should be allowed to use my super tools. And it's like, guess what, punk? Get light bulbed. Because these questions are super hard to do with those kind of analyses. Because you don't really ever build circuits like this. Okay, let's look at this one. So we have another student that says, bulb 7A, or bulb A, as I've drawn it, bulb A gets all of the potential difference across one battery. This is another student statement. Bulb A gets all of the potential difference of one of the batteries, while bulbs 7B and 7C have to share the potential difference of the other battery. Therefore, bulb A will be the brightest. The student's argument is that bulb A is dropping because at the... We doing this again? It's got something to do with, like, I wish I could tell what OneNote was ever doing. Okay, I'll just restart it. It's fine. So bulb A, the student's argument is that if I start at the pink point right here, if I look in this little section, bulb A has dropped all of the voltage from the battery below it, and then B and C must drop all of the voltage from the voltage source above that. Is there anything fundamentally different about this config versus putting all three in a row? That's a great question, Maggie. Let's find out. The student's response is that bulb A sits in here and is going to drop all the voltage across the battery. Bulb B and C must then drop the other battery's voltage. So clearly bulb B, and C must be less bright than bulb A. Let's go build it, because that's all we ever do in here. So let's turn current off, and let's just disconnect some stuff and see what we got. So what do I got? What I had before was disconnect that. I need another light bulb out here for bulb B and C. I need to get rid of this. Okay, let's just make sure that this looks like what we had over there. So I have two batteries that are oriented the way I want them to be, with a bulb in the middle, and then I have two light bulbs on the other side. So let's connect this circuit and see what happens, shall we? So we're going to connect this circuit, and what's going to happen? I'm like baiting the point. What's going to happen? Am I going to release it? Of course they all light up the same. Of course they light up the same. Why wouldn't they? They're all in a circuit together. Maggie's point is exactly correct. There's nothing different about this circuit than there is about the three light bulbs just being in series after the two batteries. Or one big battery with three light bulbs in series. Again, for like the fifth time, there's no way to analyze an individual circuit. You can't look at an individual segment. You have to go around the whole loop. So if I go around the whole loop, starting at the orange point, I'm going to gain a V0, I'm going to lose a VA, I'm going to gain a V0, I'm going to lose a VB, and I'm going to lose a VC, and that better be 0. Where these are in this equation, this is just algebra. I can move this VA over here, and nothing changed about my math. That corresponds to the VA light bulb actually being here. And there's nothing different about the two of them. And I will actually be back in just a minute. Do you want to like sit here and say hi or something for a second?
Sure.
I just have to go to the bathroom real quick. I mean, no one's watching anyway, but I'll be back to do more if you just want to like whatever, say hi.
I love squiggles. Draw squig. I really like this. I've never done circuit. I vastly prefer it to having done circuits in a non in the writing a bunch of equations way. It's awful. But I was gonna draw squigs. Oh, okay. Yeah, this works. Let's draw a little circuit monster. Don't like how thin that pen is. Get chonky. Little circuit monster. Beep, 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 beep. Beep, beep. Got some eyes. We got a little resistor, light bulb mouth. We could give him an inductor hairdo. And what else can we give our little circuit guy? Oh, here, we're gonna change it. Okay, so we're gonna have two light bulb eyes. And we're gonna have, don't like the capacitor mouth that way. Let's erase it. Okay. And then we're gonna have yeah, I'm liking this. Should the inductor be the mustache? Mr. No. Oh, I'm a genius here. Not Mr. Sir. Cut. This is Sir Cut. And what else? What else does Sir Cut need? Hmm. I drew you a guy.
Thank you. Oh, this is Sir Cut? Oh, Sir Cut is adorable.
Yeah, he's got.
Hell yeah. How's it going, Sir Cut? You are gorgeous. He's got an inductor for a mustache. I love it. Oh, this is gorgeous. I'm into it. Thank you, Maggie, for covering. Okay. I don't want to delete Sir Cut. I'll just scroll down. Okay, I feel at least one or two more circuits in me. Let's get to... Oh, let's at least do one of my favorite circuits in the whole class. We'll at least do this one because I think this is a damn blast. All right. Ooh, I have not been drawing circuits in orange. Circuits are not allowed to be orange. Circuits are purple. All right, this will be a good one too, Maggie. If you're want to have some fun with it. I got bulb A. I got 2 voltage sources in here. And the question is, what happens to the brightness of bulb A when I close the switch? What happens to A when I close the switch? Well, I mean, under normal circumstances in an actual course, this is about the time that I would be soliciting some answers as to what would happen to A when I close the switch. Not to put you on the spot, Maggie, but what do you think's going to happen here? You're saying the light bulb won't light up at all when I close the switch? So it's certainly bright before I've closed the switch, and I think everyone can agree on that, right? The light bulb A must be dropping 1 V-naughts worth of potential, and there's no real way around that. When I close the switch, I mean, it's kind of hard to, like, see what's going on here, right? What do you mean redraw it? Do you not like the way it's drawn? Okay. Let's just build it and see what it does and see if we can explain it afterwards. So let's do, I've got a battery here and I had a battery over here. I think it was, are they oriented this? I think they're oriented the same very specifically. I'm going to put a light bulb in the middle of them. I'm going to connect a wire here and a wire here and a wire here down to this battery. Go away, current. No one loves you. Okay, so here's my light bulb. And I'm just going to draw this as, like, boxy as possible, right? And I'm actually going to put a physical switch in there even, just to be even more, like, pedantic about it. Because I can be. Not allowed. Bulb stays in the middle. No, I'm keeping it exactly as posited, right? Let's connect it first and see what's going to happen. Our model tells us that what should absolutely happen, at least at the get-go, is that this thing should be bright. And of course it is. Because, of course it is. There's current flowing. You've got a resistive element and a battery in circuit with one another. Well, let's see what happens when we close the switch.
changed.
Nothing's happening. And you know, why that's happening is actually really nice to see with what's happening with the current. Because well, actually, let's get to the current in just a second. I mean, close the switch and do your loop laws, right? I have a V naught over here. And so from loop 1 in here and loop 2 in here, and I could do the outer loop, but the outer loop is very, very uninteresting if anyone's paying attention. So inner loop, because you go up an escalator and down an escalator, so it's pretty boring. If I look at, so once the switch is closed, if I look at loop 1, it's a big pen. V naught plus VA equals 0. VA. And, you know, depending on the orientation that I go about things, if I do this in the correct order, then V naught, I'm going to gain V naught, and I'm going to go over VA, and that's going to be equal to 0. So it looks an awful lot to me like when I close the switch, VA is still dropping a V naught's worth of voltage. And that is precisely because when I close the switch, the two batteries now split the current. And this is, in fact, how you make the power draw out of a battery smaller. If you've ever seen batteries in series inside of a remote or something, it's because what you're doing, the more batteries you put in series, the lower the current draw out of each one individually becomes, such that you don't overload any of the individual batteries, even while supplying a really large, you're supplying 1V worth of voltage. But you're reducing the current load on each of the battery, therefore reducing the wattage that each battery is outputting to make them last longer.
So your battery.
Mm-hmm. This doubles the lifetime of the battery, and the more batteries you put in sequence, the longer their lifetime is.
But so I could use one battery. So it's only changing how often.
This is literally a battery longevity increaser, which is why that you see it in a lot of your everyday battery devices. They put multiple batteries in there just so you have to change them out less often.
But I still have to buy 2 batteries.
True. It's also making them less likely to explode. So usually you do this in devices that have much higher current draw than these batteries are capable of actually outputting. Simply because you don't want them to blow up. So this is a cool circuit. I really like this one. Obviously, nothing happens to the brightness because the current is just being split among the two batteries, which is kind of fun. Okay, let's do one more, because there's one more fun one in here, and I wanna find the one that's fun. This is a bunch of practice, so let's do the mega ultra nasty circuit. Last circuit for the day, and then we're gonna be done. Mega ultra nasty circuit. Yeah, follow along with me on this one, Maggie. Let's see if you can do this one. I'm not like trying to quiz you and make you feel foolish, but this is really fun. This is fun for me because you well, you just you're closer in like memory to not having worked with circuits in a long time than I have. So like I know the answer to most of these right off the top of my head because I've taught this studio like 9 times. Anyway. So, I have I'm going to call this V1, and I'm going to call this V2. I should erase it. I just want to scribble it out. And I'm going to call the light bulbs A and B. And the question at the very least is, what's going to happen to the brightness of A once we close the switch? And then, what will happen to bulb B once we close the switch? Well, can we say anything about bulb B right now? Looks to me like bulb B is not going to be lit because there's no capacity for it to be in a continuous circuit right now. Bulb B is not in a connected circuit, so it should not be bright at the beginning. Bulb A will have some brightness because it's just connected to V1, right? So bulb A is going to be somewhat bright. Bulb B will be not bright at all.
Identical to the.
This is, we put an extra light bulb in, yeah. So I'm going to stop that. I'm going to disconnect this here just so that we don't have any and I'm going to disconnect that here. Okay. So we're going to put another light bulb in here and we're going to disconnect the switch so that nothing should happen there. Congratulations. And so even if I connect that, we still have that bulb's worth of brightness. So Your argument is that this is going to look identical to this case up here, Maggie, just with this extra light bulb. Is that what you were saying? Okay. So what's going to happen to bulb A when I close the switch, and what's going to happen to bulb B when I close the switch? Is bulb B going to get brighter or stay the same? Bulb B will turn on. Will it be less bright or more bright than A? So you're saying bulb A will be brighter than B, but B will turn on. Okay. Let's connect the switch, shall we?
What? Hold on. Broken.
It's not broken. I mean, let's look at the current.
Wait, but in the
Do the outside loop.
Okay, but in the other situation, the other battery did, like, the current did come out of this,
Yes.
but it doesn't come out now?
Let's do the outer loop. What do we get? Let's start at the orange point and do the outer loop. Once again, all you have is loop laws, and until you do the loop laws, you can't say anything. So I'm going to gain a V1.
Yeah?
I'm going to lose a VB.
Yeah?
And I'm going to lose a V2. What's VB? If they're identical battery sources.
0.
VB is 0 once the switch is connected. If I look smug, it's because I do this to all of my students. They all get this prediction wrong too. Because this is a really, really difficult prediction to make. This is nasty to try and do.
By putting block off.
Yes.
I'm glad the camera.
The statement was, if I put another resistor in my circuit before this battery on the separate branch, I've blocked off use of this battery. And it very much has to do with the orientation of this battery. If I flip this battery around, let's flip V2 and see what happens. If I flip V2, then this equation becomes V1 plus VB plus V2 equals 0. It looks to me like B is dropping quite a bit, right? B is going to drop then 2 V naughts, right? So what's going to happen to bulb A if I flip V2 around and connect the circuit? Maggie says nothing will happen to bulb A. It will stay the same. Well, let's check, and then we'll check our prediction afterwards. So, boop. Okay, so that is now, let's just disconnect the switch too. Okay, so now what I did is I'm flipping this battery around, and I'm going to connect that, and of course nothing is going to happen yet, and even still, nothing will happen out here except this bulb will light up. And I'm going to close the switch, and we're going to see what happens. So our prediction, just to say, is that bulb B is going to get very bright, and it's going to be brighter than bulb A was in either case. And Maggie said A will get what? What will happen with A?
Stay the same. Haha, I was right. It stayed the same.
It stays the same for a reason that's not very obvious.
Well, because it's still only hooked up.
This loop here is the same.
That loop didn't change.
Correct. This loop has not changed. This loop in here has. And actually, if I have to run the other way, because I need to gain a V naught, I'm going to lose 2 V naught over B, which means I need to gain over VA. And so what has actually happened is the current has swapped direction. So if I do this and now connect the battery.
Wait, that's just gonna ruin that one battery though, right?
So the current is still going in the same direction here. Conventional current, please. So the current, here. Flip, there we go. So the current is moving in this nice clockwise direction here, nice and positive, still going. And I close the switch. This inner section of the loop has remained unchanged, but now the current is running twice as fast on the outer loop as it was before, so that there's enough to split off and run to that light bulb and keep the current across that light bulb the same.
Is it the current moving twice as fast, or?
Well, I mean, those are the same thing. So yeah, the current, there's twice as much current as there was before, because in this outer loop, I mean, the outer loop is weird, right? I mean, you have to drop 2V0 and there's 2 batteries. So you know, you've doubled the voltage, which means you've doubled the current on the outside if you're treating these things as ohmic. So spooky. I swore we had an even harder version of this one. But I think that's actually going to be it for today. We've talked about some cool circuit stuff. So, all we've done today, and really the thing I set out to do today, which I think I've accomplished to some degree, is we wanted to set up a small model for how circuits behave. And the way that we did that is simply by adding light bulbs into circuits. And we said, all right, light bulb in a circuit is going to get bright if there's a potential difference or a current across it. And then we introduced some voltage diagrams, which I never drew because I always forget to do them. So, sue me. We introduced 2 laws, or 2 rules about how to handle circuit diagrams. But we did not say anything about Ohm's law. We did not say anything about mesh analysis. Like, there's none of this electrical engineering stuff in here. All of these things are purely laws about what happens with light bulbs. And then we simply did a million test cases with this stuff. This is, by the way, this website is the FETs. These are the education tools designed by University of Colorado at Boulder, Colorado at Boulder, whatever it's called. This is designed by their physics education research department. They are wonderful people out there designing really wonderful things. We're going to use these FETs a lot around here because they're awesome tools and they really help you learn physics. And if you have the opportunity to include this in your learning or in your education, if you are an educator in physics, these are wonderful tools. So if you've never messed with them before, they're really, really excellent. Yeah. So I think we set out to do what we wanted to do today. Excellent. All right. Well, this has been Brenden for Physics University, talking about circuits and our simple model for circuits. And we'll have more content maybe tomorrow. I don't know if we're still doing Friday stuff. We'll find out tomorrow morning because that's how life works in quarantine. And then we'll have maybe some more stuff over the weekend. And I'll at least be back next week for another lecture about whatever the hell I want because that's what life is like now. Yeah. Life's too short to not do what you want. So hopefully, and I wanted to do circuits. So, yeah, I hope there was some valuable information out there in this. There we go. That helped you understand circuits a little bit better, especially if you've never thought about circuits before at all. But even if you have thought about circuits quite a bit, the light bulb formalism is pretty fun, and you get surprisingly deep analysis out of a very simple tool. Yeah, stick around for more content from Physics University, and if you're ever interested in coming and hanging out on our streams, you can look at our schedule beneath this VOD or in the description on our YouTube channel. So yeah, stay safe everyone, and we'll see you next time. Bye bye.